Alright, today I'd like to consider problem 3.4. Let's see, it's a mass balance problem. Consider a cell with 3 species. Develop a dynamic model for species A, B, and C in a cell using the following assumptions. The effective volume of the cell is V. The cell may be assumed to be constant volume and well mixed. Species A enters the cell due to diffusion, where the total rate depends on the external concentration of A, which is Ca0. The total diffusion rate of A into the cell is dA quantity Ca0 minus Ca. B and C do not diffuse in or out of the cell. A reacts to form B with a total reaction rate of this. A also reacts to form C with a total reaction rate of this. B can react to form C with a reaction rate of this. And C decomposes inside the cell with this reaction rate. So I have 4 different reaction rates. They're total reaction rates. They're moles per minute. The diffusion rate is moles per minute. So we're going to have all the units on our mass balance in moles per minute. And let's see, we should probably draw a picture though to start out thinking about this one. What have we got? 3.4. We have a cell. We have a diffusion rate of A into the cell. It's diffusing, so it can go either way. We're going to assume it goes in. And that's J sub A, J of T, I think it is, just J. And that value was dA Ca0 of T minus Ca of T. Inside the cell we have A, B, and C. And there's we have 4 different reactions. A reacts to form B. With reaction rate 1. A also forms C. I think B forms C, and C just decomposes. If this is R1 and R2 and R3, maybe I've got the numbers wrong. This is R2, this is R3, and C is R4 for decomposition. And the total volume in the problem is V. What happened there? Move closer, it's better. This is terrible. There we go. Higher is better. All right. So we've got that part of the problem. We have nothing diffusing out of the cell, just A going in. We have 3 species, 1 volume. We're not going to model anything outside here. So our accumulation rates for the 3 species are going to be V dCA dt, V dCB dt, V dCC dt. And those should all be in units of moles per minute. The diffusion rate of A into the cell, flow of A in the cell is given in the problem, is dA Ca0 of T minus Ca of T. So we have to know the concentration of A outside the cell, we have to know the area of the cell, and the diffusion rate coefficient to actually model this. What does A do? Well, it reacts to form B and it reacts to form C. So the total reaction rate for forming B is K1 Ca of T. And A also reacts to form C. The total reaction rate for reaction 2 is K2 Ca of T squared. Those are both consuming A, so they have negative signs. We have positive sign for this diffusion rate because it's coming into the control volume. Now, for species B was created in one of those reactions. So A reacts to form B with K1Ca as the reaction rate. So K1Ca of T is forming B. Let's put a positive out front. It doesn't hurt to have that extra positive to show that every time A is consumed, we're making a B. B reacts to form C with a total reaction rate of R3. So we're consuming B at this rate, K3 Cb of T. Now B doesn't leave the cell or enter the cell, it just is produced from A and converts to C. Now, C, species C, we have to figure out what else is going on. A is forming C with that rate K2 C of T squared. But B is also forming species C with the rate K3 Cb of T. Where does all that C go inside the cell? It has to leave, so we put down a negative sign. It's not leaving, it's being consumed with this other side reaction, K4 C sub C of T. And these reaction pairs usually go together. If we're consuming A in one reaction, we're generating something else in a different reaction. We're consuming A in this reaction, and we're generating C in this reaction, 1 to 1. We're consuming B in this reaction, we're generating C in this, going from B to C in this reaction. This is a decomposition, so it's probably decomposing into something else, but it's a species we're not worried about, so we don't have to model the decomposition products. We don't have any information about that, so we can't try and model it. So our overall balance equations are just 3 differential equations where we have to understand the reaction rate coefficients, K1 through 4, the area of the cell, the effective volume of the cell, and the diffusion coefficient. So if we have those parameters, we could try and simulate this species, or we could look at doing steady state analysis where we assume all of the rate of change for the different concentrations is 0 at steady state, and look at the steady state values for Ca and Cb and Cc. We could solve those equations and actually be nonlinear because we have Ca squared in this case. So there's a few different things we can use this model for if we were interested.